The solar system looks small when we look at the drawings in school books, but the truth is very different. When scientists calculated how long it would take to leave our little corner of space, the result was mind-blowing. We're talking about thousands and thousands of years of travel, even using the fastest spacecraft we've ever built. The Voyager 1 probe, which was launched more than 40 years ago, still hasn't completely left the solar system. This made scientists ask a scary question. Is humanity trapped here forever? Get ready to fall asleep while listening to this video and discover the secrets of our cosmic neighbourhood. Subscribe to the channel, leave your like and comment where in the world you're watching from. Get comfortable and relax. Let's begin. Imagine for a moment that the classic poster of the solar system on your classroom wall, with the planets lined up neatly like marbles on a track. It is a beautiful and complete lie, a comforting illusion that utterly distorts the reality of the empty, staggering desert we actually live in. That cosy, compact neighbourhood is the first and greatest misconception we must shatter if we want to understand what escaping it truly entails. The real solar system is not about the planets themselves, those colourful dots. It is about the yawning chasms of nothingness between them. To talk about leaving, we first have to grasp just how much space we're already lost in. Our standard measure for this internal vastness is the astronomical unit. 1 astronomical unit is the average distance from the Earth to the Sun. That is a clean, simple number to write down, 1. But to translate that into a distance a human mind can feel, it is roughly 150 million kilometres. A commercial jet flying at a constant speed non-stop would need about 17 years to cover that single unit. That is just the starting line, the basic step for measuring our cosmic backyard. From that perspective, let us walk through the neighbourhood. The Sun, if we could hold it, is the only thing with any real bulk. Mercury orbits at about 0.4 astronomical units from that fiery heart. Venus orbits at about 0.7. Our Earth, of course, at 1. These are the inner suburbs, relatively speaking, but then the gaps begin to stretch. Mars is out at 1.5 astronomical units. Already the distances are becoming ungraspable. The asteroid belt, often pictured as a dense, dangerous field of tumbling rocks, sprawls from about 2.2 to 3.3 astronomical units. In reality, the asteroids are so spread out that a spacecraft navigates through without ever worrying about a chance collision. This is where the emptiness truly begins to announce itself. Next is the king of the planets, Jupiter. It orbits at a distance of 5.2 astronomical units from the Sun. That is over 5 times the Earth-Sun gap. If the Sun were the size of a soccer ball placed at the centre of a standard penalty spot on a football field, Earth would be a tiny peppercorn orbiting about 26 metres away. Jupiter, a marble, would be orbiting over 130 metres out near the opposite goal. But we're just getting warmed up. Saturn, with its glorious rings, is almost twice as far again, at 9.5 astronomical units. On our soccer field scale, Saturn is a smaller marble over 230 metres away, far out into the parking lot. Uranus and Neptune, the ice giants, recede into a profound cold. Uranus is 19 astronomical units out. Neptune, the official last major planet, is 30 astronomical units from the Sun. On our field, Neptune is a frozen pea almost 800 metres distant, requiring a long walk across several other sports grounds to find it. This is the picture most people have. 8 planets out to Neptune. This is the diagram, and this is where the lie becomes most dangerous, because it implies that past Neptune you're basically out. You've escaped. The reality is so different it is almost funny. Past Neptune lies the Kuiper Belt, a disc-shaped region of icy bodies, home to Pluto and countless other dwarf planets and objects. This belt extends from about 30 to 55 astronomical units, so already the solar system is twice as wide as the Neptune orbit suggests. But even the outer edge of the Kuiper Belt is not the exit, not even close. We now enter the realm of the truly distant, the domain of the hypothetical, the Oort cloud. This is a spherical shell of icy planetesimals, the leftover rubble from the solar system's formation that is believed to envelop everything we have discussed so far like a vast, thin bubble. Its inner edge is speculated to begin at around 2,000 astronomical units. Let us write that out. 2,000 times the distance from Earth to the Sun. Its outer boundary, where the Sun's gravitational influence finally fades to nothing against the gentle tug of the galaxy and other stars. They extend to 100,000 astronomical units. To comprehend this, we must switch units again. 1 light year is about 63,241 astronomical units. So the outer Oort cloud stretches to roughly 1.6 light years from the Sun. This is the true gravitational territory of our star. This is the prison walls. Escaping the solar system does not mean crossing Neptune's orbit at 30 astronomical units. It does not mean crossing the Kuiper belt at 55. It does not even mean crossing the heliopause, where the Sun's solar wind stalls against interstellar space, which the Voyager probes have done at about 122 astronomical units. That is just stepping out of the house and into the front yard. True escape means traversing the Oort cloud, a journey of tens of thousands of astronomical units, through a region so empty and dark it makes the space between planets seem crowded. Let us put a spacecraft into this landscape. The fastest human-made object ever is the Parker Solar Probe, but that speed is achieved falling toward the Sun. For outward-bound speed, we look to New Horizons, which flew by Pluto. It left Earth at a blistering pace, about 16.26 kilometers per second. That is fast enough to get from New York to Tokyo in about 8 minutes. At that speed, it took New Horizons 9.5 years to reach Pluto, which is only about 39 astronomical units away at its closest. The Voyager 1 probe, launched in 1977 and using gravitational slingshots, is moving at about 17 kilometers per second. It crossed the heliopause in 2012. It is now over 163 astronomical units away, and it is utterly, completely still inside the solar system. At its current speed, Voyager 1 will take about 300 years to reach the inner fringe of the Oort cloud. To pass through it completely and emerge into genuinely unclaimed interstellar space will take roughly 30,000 years. 30,000 years. Human recorded history is only about 5,000 years old. This probe, our most distant ambassador, will still be navigating the Sun's distant territory when human civilization may be unrecognizable. This is the scale. This is the first fundamental answer to how do we escape. We do not quickly, not with anything we've built so far. The propulsion challenge is monstrous because the distance is monstrous. Any realistic concept for an interstellar mission, even to our nearest stellar neighbour Proxima Centauri, which is 4.24 light years away, must first solve the problem of getting through our own backyard in a reasonable time. If it takes a spacecraft 30,000 years to clear the Sun's influence, the additional 4 light years to the next star is almost trivial in comparison. The Oort cloud is the real gate, and it is a gate a light year and a half thick. So what does this mean for escape? It means we need speeds that are not just increments better than chemical rockets. We need velocities that are a significant fraction of the speed of light to make the Oort cloud crossing a matter of years or decades, not millennia. At 20% of light speed, a craft could theoretically cross from the orbit of Neptune to the outer Oort cloud in about 8 years. That changes the entire problem. Suddenly, the vast emptiness becomes a manageable, if still huge, distance. The discussion then shifts from pure distance to the physics of achieving such speeds, protecting a craft at such velocities, and slowing down at the destination. But before any of that, we must internalize the sheer size of the territory. The solar system is not 8 planets. It is a star, some debris in the inner zone, and an immense diffuse cloud of ancient ice stretching a quarter of the way to the next star. Our sense of proximity is a cognitive illusion born of diagrams drawn to fit on paper. The truth is a crushing, exhilarating emptiness. To dream of leaving, we must first accept that we're already and always adrift in an ocean far wider than our ancestors could have possibly imagined. Our planet is a speck in a speck's orbit, within a sphere of influence so large it defies daily language. The scale is the first prison wall, and understanding its true dimensions is the first step to looking for the door. Every model you have ever seen is wrong because it has to be. To show the solar system to scale on a screen, you would need a screen miles wide, and the planets would be invisible pixels. This is not a failure of education, but a necessity of communication. We compress to comprehend, but for the purpose of escape, we must uncompress. We must replace the tidy orrery with the dizzying reality. The empty space is not just a backdrop for the planets, it is the main character. It is the antagonist in our story of departure. This emptiness is why generation ships are not just a cool idea, but a potential necessity for slower journeys. It is why sending robotic probes is a multi-generational commitment. It is why the term interstellar travel feels like science fiction, because our baseline, our normal, is this misleading compact diagram. The voyage of the Voyagers is the most humbling lesson in this. They are celebrated as having entered interstellar space, and technically they have, by one useful definition concerning the solar wind. But by the gravitational definition, the true measure of dominion, they are infants who have just begun a crawl that will last longer than our species' history. Their silent, plutonium-powered trek is a monument to both our ambition and our insignificance within the scales we inhabit. They're escaping, yes, but at a pace that renders the word almost meaningless from a human perspective. They're a message in a bottle, not a planned expedition to a destination. So, if we want to truly escape, to deliberately send something to another star within a human lifetime, we must first defeat the distance inside our own home. We must find a way to shrink the Oort cloud from a 100-millennium barrier to a manageable leg of a journey. That task begins not with building a better engine first, but with burning the misleading poster in our minds. We must see the solar system for what it is. A tiny, bright island in a vast, dark sea, surrounded by a shoal of icy rocks that extends so far it blurs the line between sea and deeper ocean. The illusion of proximity is the first chain to break. So those silent, plutonium-powered treks of the Voyagers, crawling through the void on timescales that dwarf civilization, are in fact our only tangible proof that leaving is possible at all. They are the pioneers, our first and so far only artefacts to have slipped the surly bonds of our sun's direct influence. But here is the critical, humbling twist in that story. They were never supposed to do that. The interstellar destiny was a happy accident, a bonus round unlocked by a combination of rare cosmic opportunity, ingenious engineering, and sheer, stubborn longevity. To understand them is to understand how our first steps into the galaxy were not a deliberate sprint, but a lucky, well-planned stumble. Their story begins not with dreams of interstellar space, but with a very specific and temporary window of opportunity here in the inner solar system. In the late 1970s, the outer planets Jupiter, Saturn, Uranus and Neptune were aligning in a once-in-every-175 years grand tour configuration. This meant a single spacecraft could, in theory, use the gravity of each successive planet as a slingshot, hurling itself onward to the next with incredible efficiency. NASA engineers saw this and designed two twin probes, Voyager 1 and Voyager 2, to capitalise on it. Their primary mission was a planetary tour, a close-up study of the gas giants and their moons that would revolutionise our understanding of the outer solar system. They were built with the technology of their time, with computers less powerful than a modern car key fob, communicating with Earth via a large parabolic dish and a transmitter running on about the same wattage as a dim refrigerator light bulb. Their power came not from solar panels, which would be useless that far from the sun, but from radioisotope thermoelectric generators. These RTGs convert the heat from the natural decay of plutonium-238 into electricity. Critically, this provided a long-lasting, steady trickle of power, but one that was always slowly fading as the plutonium decayed. The plan was brilliant. Voyager 2 launched first, in August of 1977, on a slightly slower trajectory that would allow it to visit all four gas giants. Voyager 1 launched a few weeks later, on a faster, shorter path that would take it to Jupiter and Saturn only, but would then get a special gravitational kick from Saturn to send it zooming out of the plane of the solar system above the ecliptic. Their journeys were triumphs of discovery. Voyager 1 revealed the volcanic fury of Jupiter's moon Io, the first active volcanoes seen beyond Earth. Voyager 2 gave us the first close-up look at the mysterious sideways spinning Uranus and its dark rings, and later the windy blue world of Neptune and its bizarre geysering moon Triton. They sent back postcards that defined a generation's view of the cosmos. The swirling storms of Jupiter, the intricate ring structure of Saturn, the pale blue dots of distant worlds. But as they completed their primary missions, their momentum carried them onward. They'd been given so much speed by their gravitational slingshots that they were now on escape trajectories from the solar system itself. They became, by default, the interstellar mission. This is where their story transitions from one of exploration to one of endurance. With their planetary targets behind them, their new mission was to probe the uncharted boundary regions where the sun's influence wanes. Their instruments, designed for studying planets, were now repurposed to sense the solar wind, magnetic fields, and cosmic rays. For decades, they flew through the heliosphere, the vast bubble of charged particles blown out by the sun. The question was, where does this bubble end? The boundary is called the heliopause, the point where the pressure of the outgoing solar wind finally equals the pressure of the incoming interstellar medium. It is not a hard wall, but a turbulent, shifting frontier. And in August of 2012, Voyager 1's instruments told a strange tale. The particles from the sun around it suddenly dropped to nearly zero. At the same time, the intensity of galactic cosmic rays from outside our solar system spiked. After months of analysis, the team concluded it had crossed the heliopause. It was now in interstellar space, bathed in material from other stars. Voyager 2, on a different trajectory, confirmed this finding when it crossed its own heliopause in November of 2018. This was a monumental human achievement. We had touched the stuff between the stars, and this is a crucial but, this does not mean they have escaped the solar system in the gravitational sense we discussed earlier. They have left the sun's weather influence, but they are still deep within the sun's gravitational well. They are still inside the Oort cloud, that immense shell of icy bodies. They have simply moved from the lively, windy backyard into the quiet, dark outer fields that still belong to the farm. Their journey now is one of pure, silent persistence. They're moving at tremendous speeds, about 17 kilometers per second for Voyager 1, about 15 kilometers per second for Voyager 2. But at that pace, as noted, it will take Voyager 1 around 300 years to reach the theoretical inner edge of the Oort cloud, and perhaps 30,000 years to pass through it completely. They're on a one-way trip with no destination star, destined to wander the Milky Way for hundreds of millions, maybe billions of years. Their greatest challenge now is time itself, in the form of decaying power. Those RTGs lose about 4 watts of electrical power per year as the plutonium decays and the thermocouples degrade. To keep the vital systems warm and the radio transmitter operating, engineers have had to make heartbreaking choices, meticulously shutting down non-essential heaters and instruments one by one. The cameras were turned off long ago after taking the famous pale blue dot family portrait. Other instruments, like the plasma spectrometer and the ultraviolet sensor, have followed. The process is a carefully managed shutdown, a slow closing of the probe's eyes and ears to keep their heart beating just a little longer. Currently they're in a phase of hard choices. Mission managers have begun turning off heaters for systems that, against all odds, are still functioning in the deep cold of space, banking on their ability to operate at temperatures far lower than they were ever tested for. The estimate is that the last science instrument will likely have to be shut down around 2035 or 2036. Sometime after that, probably before 2040, there will no longer be enough power to keep the radio transmitter going. At that point, each Voyager will become a silent, dead artifact. They will continue their trajectories, but we will never hear from them again. Their final legacy, however, will continue to travel with them. Each probe carries a golden record, a 12-inch gold-plated copper phonograph disc. It is a time capsule, a message to any distant future finder. It contains sounds of Earth thunderstorms, oceans, animals, and human greetings in 55 languages. It has music from around the world, from Bach to Chuck Berry. It has encoded images showing our planet, our anatomy, our science. The records include a cartridge and a needle with symbolic instructions on how to play them. They're a testament to the hopeful, romantic side of the mission, a deliberate attempt to cast a bottle into the cosmic ocean. The chances of them ever being found are infinitesimally small, but they serve as a poignant reminder of why we sent them. Not just to discover, but to declare, we were here. The Voyager missions teach us several profound and practical lessons about escape. First, they prove that gravitational slingshots are our only free lunch in propulsion, the indispensable trick for building up the speed needed to even think about leaving. Second, they show that longevity and reliability are as important as speed. A slower functioning probe that lasts 50 years will go much farther than a faster one that dies after 10. Third, they highlight the immense duration involved. We have been tracking these two craft for nearly half a century, and they're only just beginning their multi-thousand-year exile within our own solar system's outer dominion. They are not a model for a deliberate interstellar mission, but they are the pathfinders. They showed us where the frontier actually lies, not at the planets, but far, far beyond. They continue to send back data from a region we can never hope to visit with humans in any foreseeable future, measuring the magnetic field and particle density of the local interstellar medium. Every bit of data is precious, the direct sampling of the galaxy. As their power fades, their signal becomes fainter. It takes over 20 hours for a signal from Voyager 1 travelling at the speed of light to reach Earth. The signal that arrives is about 20 billion times weaker than the power of a digital watch battery. Massive radio dishes of the Deep Space Network with their sensitive receivers must listen intently to pull that whisper from the cosmic static. Soon, that whisper will stop. But the Voyagers themselves, these 800-kilogram bundles of ancient technology, will keep going. They will outlast the pyramids, outlast human languages, outlast perhaps even the continents on Earth. They are our most durable creations, destined to become the quietest, most distant relics of a species that once looked up and wondered. They're not escaping to anywhere. They're simply escaping, proving that the door out exists, even if the walkway beyond is longer than we can truly comprehend. Their greatest achievement may ultimately be not the data they sent back, but the simple, staggering fact of their continued journey, a perpetual monument to a moment when humanity reached for the stars and, against all odds, managed to let go. So those silent voyagers, our most distant emissaries, have passed a major milestone, but they are not free yet. They have left the house, so to speak, but they're still wandering the vast, dark fields of the farm, fields that stretch so far that the farmhouse light is just a distant speck. That farm, that final and truly daunting domain, has a name, the Oort Cloud. This is not a place you can see or visit. You'll never get a postcard from there. It is a theoretical realm, a ghostly shell predicted by astronomy, and it represents the ultimate gravitational fortress of our solar system. To escape the sun's grasp for real, you must traverse this. The heliopause that the Voyagers crossed, that boundary of solar wind, is important, but it is a weather front, not a border. The real border is where the sun's gravity finally becomes too weak to hold on to things, where the gentle tugs of other passing stars and the galaxy itself become dominant. That border is defined by the outer reaches of the Oort Cloud. So what exactly is it? Imagine taking every icy leftover from the solar system's formation, every cometary nucleus that never got baked into a planet, and throwing them into a gigantic spherical cloud that envelops everything. That is the Oort Cloud. It is not a flat disk like the asteroid belt or the Kuiper belt. It is a shell, a swarm, a cosmic halo of perhaps trillions of icy objects orbiting the sun in all directions. Its inner edge is thought to begin at around 2,000 astronomical units from the sun. Remember, Neptune is only 30. The Voyagers, now just over 160 astronomical units out, have not even come close to the starting line of this place. The outer edge of the Oort Cloud is where the solar system truly ends. Estimates vary, but it could extend to a staggering 100,000 astronomical units. To put that in perspective, 1 light-year is about 63,241 astronomical units, so the Oort Cloud could reach out about 1.6 light-years from the Sun. That means the true diameter of our solar system, from one side of this cloud to the other, could be over 3 light-years. Proxima Centauri, our nearest stellar neighbour, is 4.24 light-years away, so the empty space between our Sun's territory and the next star's territory is, in some places, less than the width of our own solar system's outer frontier. That is a mind-bending fact. The solar system is mostly this cloud. We live in a tiny, bright, dense little bubble in the centre of an immense, dark and almost empty sphere. How do we know it is there if we have never seen it? We see its children. Comets are the key. Astronomers classify comets into 2 main groups, short period and long period. Short period comets, like Halley's Comet, orbit the Sun in less than 200 years and come from the Kuiper belt, that disk beyond Neptune. But the long period comets, the ones with orbits lasting thousands or even millions of years, they come from somewhere much farther away. The orbits are highly elliptical, diving in from all angles, not just from the plane of the planets. This told the Dutch astronomer Jan Oort, who proposed the cloud in the 1950s, that there must be a vast spherical reservoir of these icy bodies. Every so often, the gravitational nudge from a passing star, or the gentle tidal forces of the Milky Way galaxy itself, disturbs one of these distant chunks of ice. It falls inward on a multi-million-year journey, eventually warming up as it approaches the sun, growing a glorious tail and putting on a show for us. That comet is a messenger from the deepest, darkest reaches of our own home. The Oort cloud is the factory, the storage vault for these spectacular visitors. Now, crossing this region is the real meaning of escape. The voyages, for all their speed, will take tens of thousands of years to get through it. Think about that timescale. Human civilization from the first cities to today is maybe 5,000 years old. The voyagers will be drifting through this silent, frozen wilderness for perhaps 30,000 years. They will not encounter a dense field of ice blocks. It is far too sparse for that. If you were on a Voyager probe, you would likely never see a single Oort cloud object, even though trillions are out there. The distances between them are still immense, perhaps tens of millions of kilometres apart. It is the emptiness that defines it, the sheer volume of space that must be crossed. This is why escaping the solar system is not a quick manoeuvre. It is a geological epoch of travel. For a human mission, this presents the ultimate problem of time. Even if we built a ship that could accelerate to say 1% of light speed, which is a tremendous technological leap, it would still take over 300 years just to cross the Oort cloud from its inner edge. That is a multi-generation journey just to get out the front door. This changes the entire concept of an interstellar mission. It means the first leg of any trip to another star is not the interstellar medium proper, but this final lingering gravitational grip of our sun. Any realistic plan must account for this. It means propulsion systems need enough power not just to get us to another star, but to get us through our own backyard in a reasonable time. This is where concepts like laser-powered light sails become so compelling. If we could accelerate a probe to 20% of light speed, it could blow through the Oort cloud in a human lifetime, making the solar system feel small again. But with any slower technology, the Oort cloud is the showstopper, the infinite waiting room. There is another fascinating aspect to the Oort cloud. It is not entirely ours. Because it is so far out, its outer regions are weakly bound to the sun. The gravity of other stars that pass nearby, and there are many over millions of years, can steal objects from our Oort cloud and vice versa. There is likely a continuous slow exchange of icy material between the Oort clouds of neighbouring stars. In a very real sense, the outermost Oort cloud is the galaxy's common territory. This blurry boundary is the true frontier. So, when we talk about the Voyagers as interstellar probes, we must be precise. They are probes in the interstellar medium, the gas and dust between stars, but they are not yet in interstellar space from a gravitational standpoint. They are still subjects of the Sun, destined to orbit it for perhaps billions of years, even as they drift through this cloud. Their signal to us will die long before they even reach the inner edge of this realm. For all practical purposes, for us, they are gone. But in the grand cosmic clock, their journey to freedom has barely begun. This understanding forces a humility about our place. We are not at the edge of something, looking out. We are in the deep interior of a structure so large that light itself takes years to cross it. The planets are just decoration near the centre. The Oort cloud is the main event, the bulk of the solar system's mass and volume, existing in a state of frozen, primordial patience. Escaping it means leaving behind not just warmth and light, but the very gravitational context of our existence. It means entering a space where the sun is just another bright star, and where the pull of the galactic core becomes more relevant than the pull of our birth star. For a spacecraft, crossing the Oort cloud is the final silent test of endurance. There are no landmarks, no solar wind to measure, just the slow, steady dimming of the sun into a point of light no brighter than many others. Navigation would rely on the distant pulsars, the lighthouses of the galaxy. Power would have to be nuclear, or something yet invented, as sunlight is useless. The temperature would hover just a few degrees above absolute zero. It is the ultimate deep freeze. This is the last redoubt, the final castle wall, and it is not a wall of rock, but a wall of distance, of scale, of time. To pass through it is to shed the last vestige of our solar system's influence. Until something does that, we are still, fundamentally, home. The Voyagers are like messages slipped under the door. They have left the room, but they are still in the hall of the house. The Oort cloud is that hall, a hallway light years long. Understanding this completes the picture of our cosmic neighbourhood. It is not 8 planets and a belt. It is a star, a sprinkle of rocky and gaseous worlds, a disk of icy debris, and then a colossal spherical cloud of ancient ice, stretching a quarter of the way to the next star. That cloud is our true context, our real estate. Any dream of escape must first be a plan to traverse that, to cross the sea of frozen time that surrounds our island of light. It is the greatest physical obstacle we face, not because it is dense, but because it is so unimaginably vast. The Oort cloud is the solar system's final lesson in scale, teaching us that home is much, much bigger than we ever thought, and that leaving it is the longest journey of all. So if the Oort cloud is the vast, daunting hallway we must traverse to leave the house, then our current method of walking is like trying to cross it on crutches. We are painfully, agonizingly slow, and the reason is not a lack of will, but a brutal, unforgiving law of physics that governs every rocket we have ever built. This is the rocket equation, and it is the single greatest technological shackle keeping us from any meaningful escape. It is often called the tyranny of the rocket equation, and once you understand it, you will see exactly why our shiny rockets, for all their fire and thunder, are barely crawling out of the cosmic cradle. The core problem is simple to state but devastating in its consequences. To go faster, you need more fuel, but that extra fuel has mass, and pushing that extra mass requires even more fuel. This creates a feedback loop of doom. It is not a linear relationship, it is exponential. Want to double your final speed? You do not just need double the fuel, you might need 4 times, 10 times, or 100 times the initial mass to be fuel. Very quickly you hit a wall where almost everything you launch is just the propellant to push more propellant, leaving almost no room for the actual spacecraft, the payload, you wanted to send on the journey. The equation that describes this was formulated over a century ago by a Russian scientist named Konstantin Tsiolkovsky. It relates the final velocity of a rocket to the exhaust velocity of its engine and the ratio of its initial mass to its final mass. The key term is the exhaust velocity. This is how fast you can throw your propellant out the back. The faster you can throw it, the more efficient your rocket is. Think of it like this. If you're on a slippery ice rink and you throw a heavy bowling ball, you will slide backward a bit. If you throw a tennis ball with the same force, you will slide much less because the tennis ball is lighter and you cannot throw it as fast. The bowling ball represents a high exhaust velocity, a lot of mass thrown backward very effectively. Chemical rockets, which are all we have used to get to orbit and beyond, have a fundamental limit to their exhaust velocity. It is determined by the energy released by burning their fuel and oxidizer. The best combinations, like liquid hydrogen and liquid oxygen, have a maximum exhaust velocity around 4.5 kilometers per second. That sounds fast, but it is the hard ceiling for chemical propulsion. You cannot make a chemical fire burn hotter and more efficiently beyond a certain point. The physics of the molecules themselves sets the limit. This limit is what makes escaping Earth's gravity so hard. To reach orbit, you need to achieve a velocity of about 8 kilometers per second. Because of the rocket equation, getting that final speed with a chemical exhaust velocity of 4.5 kilometers per second requires a massive amount of fuel. Look at the Saturn V rocket that went to the moon. It was over 100 meters tall. Most of that height was fuel tanks. The actual Apollo spacecraft that housed the astronauts and landed on the moon was a tiny fraction at the top. That is the tyranny in action just to get to our nearest celestial neighbour. Now, apply this to escaping the solar system. You need even more speed, not just to leave Earth, but to leave the sun's gravitational pull from Earth's distance. That solar escape velocity is about 42 kilometers per second, but because we're already orbiting the sun at 30 kilometers per second, we need an extra push of about 12 to 16 kilometers per second from Earth's orbit. That is the target. To get a useful payload to that speed with chemical rockets is where the dream runs into a brick wall. Let us take our fastest interstellar projectile, the New Horizons probe, to Pluto. How did we get it going so fast? We used a giant rocket, an Atlas V with 5 solid rocket boosters and a third stage to give it a tremendous kick directly from Earth. Even then, its launch mass was over 470 kilograms, but the probe itself was only at about 478 kilograms. The rest was the third stage motor and adapters. It left Earth at about 16 kilometers per second relative to Earth, the fastest launch ever. But here is the catch. That speed was largely about escaping Earth quickly to get to Pluto in a reasonable time. Its speed relative to the Sun was not much faster than what the Voyagers achieved with their gravity assists. To go significantly faster, say to double or triple that solar system exit speed, with a chemical rocket launched from Earth, the numbers become absurd. You would need a rocket of such immense size that building it would be like building a skyscraper that is almost entirely fuel tanks, with a payload the size of a car at the very top. The mass ratio, the initial mass divided by the final mass, becomes astronomical. The equation mercilessly shows that to reach higher final velocities with a low exhaust speed, the mass ratio must grow exponentially. To achieve a final velocity twice the exhaust velocity, the mass ratio might need to be around 7 or 8 to 1. To achieve 3 times the exhaust velocity, the mass ratio might skyrocket to over 20 to 1. Since our exhaust velocity is capped at 4.5 kilometers per second, and we need a final change in velocity far greater than that to do anything interesting for interstellar travel, we are stuck. This is why all concepts for interstellar travel start with the same premise. We must abandon chemical propulsion. It is a dead end for this purpose. It is perfect for getting us into orbit, for quick trips to the moon, even for sending probes on decades-long journeys to the outer planets with gravity assists. But for breaking free, for crossing that Oort cloud in less than millennia, it is useless. We need a way to throw our propellant out the back much, much faster. We need a higher exhaust velocity. This is where the conversation turns to other technologies. If you can double your exhaust velocity, you dramatically reduce the required mass of fuel for the same final speed. This is the quest. Electric propulsion, like ion thrusters, does this. They use electricity, often from solar panels, to ionize a gas like xenon and accelerate the ions out the back with an electric field. Their exhaust velocity can be 10 times higher than chemical rockets. But they have a different problem. Extremely low thrust. They are like a feather pushing against a brick wall. It takes them months or years to accelerate to a high speed, but they are incredibly fuel efficient. They're great for nudging satellites around in orbit or for slow, steady missions to asteroids, but for launching from Earth or for a quick escape from the Sun's gravity well, they're too weak. You would need a colossal amount of electrical power to get a high thrust from an ion engine. Nuclear thermal propulsion is another candidate. Here, a nuclear reactor heats a propellant like hydrogen to extreme temperatures and blasts it out a nozzle. The exhaust velocity could be about twice that of the best chemical rockets. That is a significant improvement. It could cut travel time to Mars by months, but it still might not be enough for a rapid solar system exit with a large payload. The mass ratios, while better, are still very challenging. And then there are the more speculative ideas like nuclear pulse propulsion, Project Orion, which uses actual nuclear explosions behind a pusher plate to propel a ship. That could theoretically reach a few percent of light speed. Its exhaust velocity is enormous because you are throwing out plasma from nuclear blasts. That could potentially beat the Tyranny for slower interstellar journeys, but the political, environmental and engineering challenges are, to put it mildly, immense. The rocket equation is not just a math problem, it defines the landscape of possibility. It tells us that with our current propulsion, the fuel needed for a human crew to make a fast trip to another star would weigh more than the entire planet. It is a non-starter. This is why all realistic designs for interstellar probes, like the breakthrough Starshot concept, aim for minimal mass. They want to send a tiny gram-weight chip, not a human habitat. Because the smaller the payload, the less brutal the rocket equation's punishment is for a given technology. The Tyranny also explains why gravity assists are so precious. They give you a change in velocity for free or without you having to carry the fuel for it. They are a loophole, a way to cheat the equation a little bit by stealing a tiny bit of a planet's orbital momentum. But as we saw, even the mighty slingshot from Jupiter only gives the Voyagers a modest push by interstellar standards. The rocket equation is the silent gatekeeper. It sits there in every mission design office dictating what can and cannot be done. Before we even dream of building a generation ship or a fast interstellar probe, we must find a way to defeat this fundamental law. Not break it. It is a law of physics, we cannot break it. But work around it by finding a propulsion method with an exhaust velocity so high that the mass ratios become manageable. Until we have that, our dreams of escape are just that. Dreams, constrained by the cold, hard math of throwing things backwards. It is the first and most important technical hurdle, more immediate than radiation or human psychology, because without solving it, we never get to experience those other problems. We stay here, forever glancing at the Oort cloud, knowing it is there, but unable to cross it in any meaningful time frame. The rocket equation is the chain that binds us to our sun, and the key to unlocking that chain is finding a better way to push. So the rocket equation demands a way to throw stuff backward much faster, or better yet, not carry the stuff to throw at all. What if you could push a spacecraft without any fuel on board whatsoever? What if the engine was external and its fuel has been streaming toward us for billions of years? This is not science fiction. It is the principle behind the solar sail, a concept that turns light itself into a gentle, endless wind. It is arguably our most plausible, physics-abiding ticket to a fast escape from the solar system, and it starts with a simple, beautiful fact. Light exerts pressure. Photons, the particles of light, have no mass, but they do have momentum. When a photon strikes a surface and bounces off, it gives that surface a tiny, tiny push. In everyday life, this push is so infinitesimal you would never notice it. A laser pointer on your hand does not shove you backward, but in the vacuum of space where there is no friction, and you can be extremely patient, that tiny push adds up. If you have a large, extremely light and reflective sheet, you can catch this light and use it to propel yourself. That is a solar sail. Imagine it as a giant, ultra-thin mirror. Sunlight hits it and reflects, giving it momentum in the opposite direction. It is a boat sailing on a sea of photons. The acceleration is incredibly small at first, far less than the gentle pull of gravity you feel right now, but it is constant. Unlike a chemical rocket that burns all its fuel in minutes and then coasts, a solar sail is pushed continuously for as long as the light shines on it. Over weeks, months, and years, that tiny, unrelenting push can build up to tremendous speeds. This solves the rocket equation's tyranny in the most elegant way possible. The propellant is sunlight, and you do not have to carry it. Your fuel tank is the sun. The performance of a sail depends on three main things: how large and light it is, how reflective it is, and how close it is to the light source. To get a useful acceleration for a meaningful payload, the sail needs to be enormous and the spacecraft needs to be feather-light. We are talking about sails hundreds of meters or even kilometers across, made of materials like mylar or polyimide that are thinner than a human hair. The entire structure might be lighter than a small car. This is where engineering meets the extreme. Deploying such a vast, fragile structure in space is a monumental challenge. It cannot be launched fully assembled. It must be folded into a tiny package and then unfurled perfectly in zero gravity. But we have already begun. Missions like Japan's Ikaros and the Planetary Society's LightSail 2 have successfully demonstrated solar sailing in Earth orbit. They proved the principle works. LightSail 2, a spacecraft about the size of a loaf of bread, used its 32 square meter sail to raise its orbit around Earth, using only sunlight pressure. It was a profound proof of concept. For escaping the solar system, however, sunlight alone near Earth is not enough to reach the speeds we need. The pressure from the sun weakens with distance following the inverse square law. Double your distance from the sun and the light pressure drops to a quarter. By the time you reach Jupiter, the push is very faint, so a pure solar sail using just the sun is fantastic for inner solar system missions and perhaps for journeys to the outer planets over long periods, but for a rapid interstellar sprint, it needs a boost. This is where the concept gets a serious upgrade: the laser sail. Instead of relying solely on the diminishing sunlight, we could build powerful lasers on Earth, or in orbit, and train them on the sail. This provides a concentrated beam of light that does not weaken over distance as quickly as sunlight. We could blast the sail with this laser for minutes or hours, accelerating it to a significant fraction of light speed, while it is still relatively close to home. Then it coasts at that incredible speed across the interstellar void. This is the core idea behind initiatives like Breakthrough Starshot, which aims to send a fleet of gram-weight probes, each attached to a sail a few meters across, to the Alpha Centauri star system within a human lifetime. The numbers are staggering. They envision a ground-based laser array with a collective power of 100 gigawatts firing at the sails for a few minutes. The acceleration would be thousands of times Earth's gravity, requiring incredibly robust tiny probes. But if it works, the sails could reach 20% of the speed of light in that short push. At that speed, the Oort cloud becomes irrelevant, crossed in a matter of days or weeks. The 4.2 light-year journey to Alpha Centauri would take about 20 years. This changes everything. Suddenly, the timescale for escape is not geological or multi-generational. It is a single human career. The probe itself, often called a Starship, would be a fully functional spacecraft on a single silicon wafer, with cameras, sensors, communication lasers, and a power source. It would be a digital astronaut weighing grams. Upon arrival, it would have perhaps minutes to fly past any planets in the system, take a barrage of images and data, and then begin the long task of beaming that information back to Earth, a process that would take over 4 years for each bit of data to travel the distance. The challenges are immense, bordering on the fantastical, yet they do not violate known physics. First, the sail material. It must be almost perfectly reflective to absorb as little heat as possible from the powerful laser, because absorption would vaporize it. It might need to be made of novel metamaterials. Second, the laser itself. Building a coherent phased array of lasers that can combine their power into a single beam that can stay focused on a sail thousands of kilometers away, and then millions, and then billions of kilometers away, is a problem of astronomical precision. The slightest vibration or atmospheric distortion could blow the beam off course. Third, navigation and survival. At 20% of light speed, a collision with a dust particle the size of a sand grain would be catastrophic. The sail would need to be incredibly durable or have a way to detect and avoid such hazards, which is nearly impossible at those speeds. The interstellar medium is not perfectly empty. Fourth, communication. How does a gram-weight probe with a tiny power source send a signal back over 4 light years that we can detect on Earth? It would likely need to use the sail itself as an antenna, focusing a laser beam back at our solar system. The engineering tolerances are mind-boggling. Then there is the sheer scale of the infrastructure. A 100 gigawatt laser array would require a massive power supply, likely spread over a large area, and would represent a significant portion of humanity's current energy output. It is a civilization-scale project. Yet, for all these challenges, the solar and laser sail concept remains the only one on our drawing boards that offers a plausible path to interstellar travel within a century. It sidesteps the rocket equation entirely. There is no need for onboard fuel, so there is no exponential mass penalty. The engine stays at home. This also means the spacecraft can be dedicated almost entirely to its mission payload, not to propulsion systems and fuel tanks. It is a paradigm shift from the brute force of rocketry to the subtle, persistent finesse of light pressure. For slower, more near-term missions within our solar system, solar sails are incredibly promising. They could enable stations that hover at unusual points in space, missions to study the sun's poles, or efficient transport of cargo between the planets. They are a technology that gives us true freedom of movement within the inner solar system without fuel constraints. For escape, however, the laser boost is the key. It represents our first realistic method for achieving relativistic speeds where the universe starts to feel a bit smaller. It acknowledges that the solar system is too big for fuel-based rockets, but perhaps not too big for a beam of light we control. The dream is to turn our entire star into a lighthouse, not just for illumination, but for propulsion, pushing our tiny emissaries out into the galaxy. It is a humbling thought. Our greatest journey might begin not with a roar, but with the silent, focused shine of 1 billion lasers on a speck of silvered film, a final, gentle push out the door. The gentle, fuel-free push of light is one answer to the rocket equation, but it is a subtle one, requiring immense patience or colossal external infrastructure. There is another, more visceral answer that does not try to sidestep the tyranny, but confronts it with raw power. We carry the potential for that power here on Earth, locked inside the atom. Nuclear propulsion is not a distant dream. It is a century-old idea that represents the next logical, albeit complex, step beyond chemical rockets. It is about using the concentrated energy of nuclear reactions to heat or electrically accelerate propellant to velocities chemical fires can never reach. This is the realm of nuclear thermal and nuclear electric propulsion, and the far more dramatic concept of nuclear pulse propulsion. These are the technologies that could give us true command of the inner solar system and make slower interstellar journeys, measured in centuries rather than millennia, conceivable. They're about building a better engine, not leaving the engine behind. Let us start with nuclear thermal propulsion, often called NTP. The concept is straightforward in principle. You have a compact nuclear fission reactor, similar to those in submarines or aircraft carriers, but designed for space. Instead of using the reactor's heat to make steam for a turbine, you run a propellant, typically liquid hydrogen, through the superheated core. The hydrogen absorbs that intense heat, expanding violently and shooting out of a rocket nozzle at exhaust velocities potentially double that of the best chemical engines. Think of it as a turbocharged steam engine, where the steam is hydrogen and the fire is a controlled atomic furnace. The improvement is significant. A chemical engine might have a specific impulse, which is a measure of efficiency, around 450 seconds. A good nuclear thermal rocket could achieve 900 seconds or more. That means it can get twice the push from the same mass of propellant, or the same push with half the fuel. For missions within the solar system, this is revolutionary. A trip to Mars, which takes 6 to 9 months with chemical propulsion, could be cut down to 3 or 4 months with NTP. This reduces the crew's exposure to cosmic radiation and microgravity, and simplifies life support. For outer planet missions, a nuclear thermal spacecraft could reach Jupiter in a year instead of 5, and Saturn in 2 instead of 7. It transforms the solar system from a series of distant outposts into a more manageable neighbourhood. The technology was actively developed and ground tested in projects like NASA's NERVA program in the 1960s and 70s. They built and fired reactors that proved the concept worked. The program was cancelled not due to technical failure, but because political priorities shifted away from advanced deep space missions after Apollo. The engineering challenges are real but not insurmountable, containing incredibly hot hydrogen, managing the reactor in microgravity, and ensuring safety during launch. But the physics is sound. Then there is nuclear electric propulsion, or NEP. This is a different beast. Here, the nuclear reactor is used as a power plant. It generates a large amount of electricity which then powers an ion thruster or a Hall effect thruster. These electric thrusters work by ionizing a propellant like xenon or krypton and accelerating the ions out with an electrostatic field. Their exhaust velocity can be staggering, up to 10 times higher than chemical rockets. The key advantage is incredible fuel efficiency. The downside is low thrust. A nuclear electric spacecraft might have the thrust of a sheet of paper resting on your hand. It cannot fight Earth's gravity to launch. It would have to be assembled in orbit. But once in space, that tiny, constant push applied for months or years can achieve very high speeds and is perfect for moving heavy cargo or large spacecraft on slow, efficient spirals through the solar system. A manned NEP ship would not feel a sudden kick. It would be a gradual, imperceptible acceleration that over time results in tremendous velocity. The main challenge is the mass and size of the power system. You need a robust reactor, heavy shielding to protect the crew, and large radiators to dump waste heat. It is a system better suited for larger, long-duration vessels, but for a slow interstellar arc, a massive nuclear electric propulsion system could provide steady, reliable thrust for centuries. Now, we come to the most audacious and controversial idea: nuclear pulse propulsion. This was seriously studied in the 1950s and 60s under this name Project Orion. The concept is shockingly simple and feels almost like science fiction. You detonate atomic bombs behind a spacecraft. Specifically, you drop small fission or fusion bombs out the back of a massive vehicle at a steady rate. They explode, and the plasma from the blast slams into a giant, heavily shielded pusher plate attached to the ship by enormous shock absorbers. The plate absorbs the momentum, and the ship is propelled forward. Then you drop another bomb and repeat. It is the ultimate in brute force propulsion. The exhaust velocity is the speed of the nuclear fireball, a significant fraction of light speed. This means it could in theory reach velocities of perhaps 5 to 10% of light speed. At 10% of light speed, you could reach Alpha Centauri in about 44 years. That is still a multi-generation ship for a human crew, but for an automated probe, it is a feasible timeline. The engineering study suggested that an interstellar Orion vehicle could be the size of a small city. With a pusher plate hundreds of meters wide, it would be assembled in orbit. The proponents argued it was feasible with late 20th century technology, so why was it abandoned? The reasons were not primarily technical, but environmental and political. Launching such a ship from Earth's surface would involve detonating hundreds of nuclear devices in the atmosphere. with obvious catastrophic fallout, even an orbital assembly and ignition would raise fears of nuclear proliferation and space-based weapons treaties. The Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear explosions in the atmosphere, underwater, and in outer space, effectively killed the original Project Orion. The societal will to pursue such a terrifyingly powerful technology evaporated. However, the physics remains compelling. Later concepts like Project Daedalus, a study by the British Interplanetary Society in the 1970s, refined the idea for interstellar travel. Daedalus proposed a two-stage unmanned probe using inertial confinement fusion pellets ignited by electron beams, eliminating the need for fission bombs. It was a cleaner, more advanced version of the pulse concept, but still far beyond our current ability to manufacture and control. The promise of nuclear pulse is that it demonstrates we already possess, in our existing nuclear arsenals, the energy density required for interstellar travel. The energy in a kilogram of fissionable material is millions of times greater than in a kilogram of chemical rocket fuel. The problem is not having the energy, it is packaging and releasing it in a controlled, useful, and socially acceptable way for propulsion. It is a technology that sits uncomfortably between a propulsion system and a weapon. Today, the focus has shifted back to the more palatable nuclear thermal and nuclear electric concepts. NASA and other space agencies are actively researching new NTP designs, with plans for possible Mars missions. Nuclear electric propulsion is considered a key technology for future cargo and deep space exploration. These systems represent a middle path between the explosive power of Orion and the gentle push of solar sails. They offer a realistic near-future upgrade that could slash travel times within our solar system and make human missions to the outer planets a possibility within this century. For escape, however, even advanced NTP might not be enough to cross the Oort cloud quickly. It would make the initial departure from the inner solar system faster, but the long coast through the cloud would still span centuries. Nuclear electric, with its high efficiency but low thrust, is better suited for a slow, steady, multi-generation arc that is in no hurry. Nuclear pulse remains the only nuclear concept with the theoretical muscle to make an interstellar journey in a time frame of decades to a century. It is the stark reminder that the energy for star travel is within our grasp, but the method of harnessing it forces us to confront profound ethical and practical dilemmas. Do we dare use the power that can destroy worlds to propel us to others? The answer for now seems to be no, which is why research continues on the less dramatic but more socially sustainable paths. Nuclear propulsion in all its forms represents a critical stepping stone. It is the bridge between the chemical rocketry that gave us access to Earth orbit and the Moon, and the future technologies like matter-antimatter drives or warp drives that remain in the realm of speculation. It is a technology that says we can work within the rocket equation by dramatically upping the energy density of our fuel. It acknowledges that to escape the well you need a more powerful ladder. While we may not be ready to build the city-sized bomb-propelled starship, the quieter, steadier nuclear thermal and electric engines could be the workhorses that first give us true freedom in our solar system, making the construction of those future interstellar arcs in the safe space of orbit a practical possibility. They turn the dream of escape from a physics problem back into an engineering and political one, which, in a way, is progress. Will they share the same commitment to a destination they will never see? Could resentment and a sense of imprisonment boil over into social unrest, or even violence? Maintaining a stable, functional and motivated society over centuries in a closed ecosystem is a problem we have zero experience with. It is a challenge of sociology, culture, law and mental health that may be more complex than the physics of propulsion. Furthermore, you have the practical problem of a closed ecological system. The ship must recycle every gram of water, oxygen and nutrient with near perfect efficiency for centuries. Tiny imbalances or system failures could lead to a cascade of collapse. We have tried small-scale versions of this on Earth, like the Biosphere 2 project, with mixed and often problematic results. Scaling this up to a self-sustaining arc for thousands is an ecological engineering problem of staggering difficulty. All these biological barriers point to a sobering conclusion. The human body, in its current form, is perhaps the worst possible vessel for an interstellar journey. We are fragile, require constant and specific environmental conditions, and are prone to social dysfunction. This realization pushes the concept of human spaceflight to its limits. It suggests that if we're to travel to the stars, we may need to change not just our machines, but ourselves. One path is transhumanism, using technology to augment and modify human biology. This could involve genetic engineering to enhance radiation resistance, slow muscle atrophy, or reduce our psychological need for wide open spaces. It could involve cybernetic implants to monitor and regulate our health. Another path is to send humans in a dormant state like hibernation or suspended animation, drastically reducing the resource consumption and psychological strain of the journey. While some animals hibernate, we do not know how to induce a safe, reversible long-term hibernation state in humans. It remains in the realm of research. The most radical solution is to abandon biological humans altogether for the voyage. We could send frozen embryos or genetic material to be gestated and raised by machines upon arrival. Or we could go fully digital, uploading human consciousness into robust computational substrates, sending our minds as information to be installed in synthetic bodies or virtual worlds at the destination. These are the realms of extreme speculation. The more immediate takeaway is that any credible plan for human interstellar travel must place biology and human factors at the very centre of the design. The ship cannot just be a propulsion system with life support tacked on. It must be a world, an ecosystem, a society and a hospital, all rolled into one, designed to coddle and protect a life form that is stunningly ill-adapted for the environment it seeks to enter. The rocket gets us out the door, but it is the mastery of our own flesh and mind that will determine if we can survive the hallways. The ultimate answer to the biological prison, then, is not to fight it piecemeal with exercise machines and radiation pills, but to build a new world that carries the prison with us, perfectly maintained. This is the Interstellar Ark, also called a generation ship or world ship. It is not a spacecraft in the traditional sense. It is a mobile, self-contained fragment of a planet, a civilization in a bottle hurled across the void. If we accept that the journey will take longer than a single human lifetime, perhaps centuries or millennia, then the Ark becomes the only viable container for human life. It is the admission that escape is not a mission, but a migration. The concept is simple in outline but staggeringly complex in detail. Imagine a structure, most likely cylindrical or ring-shaped, several kilometres long, rotating to provide artificial gravity via centrifugal force on its inner surface. Inside you would find not just crew quarters and control rooms, but forests, streams, farms, towns, and a fully functioning ecosystem. It is a biosphere under a dome, with a fusion reactor or some other immense power source as its tiny artificial sun. The scale is incomprehensible by today's engineering standards. This would be the largest structure ever built by humanity, constructed not on Earth, but assembled in space, likely using materials mined from asteroids or the moon. The primary purpose of the Ark is to create a stable, sustainable, and healthy environment for thousands of people across dozens or hundreds of generations. Every single aspect of Earth's life support must be replicated and maintained with near-perfect reliability. The air must be constantly scrubbed of carbon dioxide and replenished with oxygen by vast arrays of plants and algae. Water must be recycled from every possible source: urine, sweat, humidity, with an efficiency of 99.99%. Waste must be broken down and its nutrients fed back into the agricultural systems. This closed-loop ecology is the heart of the Ark, and we have no proven model for one on this scale or for this duration. Experiments like Biosphere 2 showed how fragile and unpredictable these systems can be, with unexpected crashes in oxygen levels and explosions of some species at the expense of others. On an Ark, such a failure could mean extinction. The social structure aboard an interstellar Ark would be a unique human experiment. The initial crew, perhaps a few thousand carefully selected individuals, would be the founders. But within a few generations, their descendants would know nothing of Earth except as history, legend, and perhaps grainy videos. Their entire universe is the Ark. Their culture, language, social norms, and even their physical biology would begin to adapt to this closed environment. There is a dark side to this. Societal stability over such timescales is a huge unknown. Could a rebellion or a destructive ideology take hold and doom the mission? How do you govern such a society? Is it a democracy, a meritocracy, a dictatorship run by the ship's AI? What rights do individuals have in a society where every action, including reproduction, might be regulated for the survival of the whole, the concept of mission might fade for those born into the journey. Would the 10th generation still care about a planet called Earth, or a destination star they will never see? Maintaining knowledge and technical skills across centuries is another monumental challenge. The ship's systems would need constant maintenance and repair. Would the knowledge of how to fix the nuclear reactor or the water recyclers be preserved intact for 600 years? Or could it degrade into ritual and superstition, like cargo cults waiting for a repair manual they no longer understand? The ship's computer archives would hold everything, but accessing and understanding that information requires a maintained educational system and cultural continuity. There is also the biological evolution within the Ark. Over hundreds of generations, in a relatively small gene pool, genetic drift would occur. Without careful genetic management, harmful recessive traits could become more common. The human body might also adapt subtly to the specific conditions of the ship, like its exact artificial gravity level, which might be less than Earth's 1G to save on structural mass, or its constant background radiation level, which would be higher than Earth's despite shielding. These Ark humans could become a distinct subspecies, potentially unable to survive easily on any natural planet at the journey's end. The risks are existential and constant. A pandemic in the closed environment could wipe out everyone. A major systems failure, like a rupture in the hull or a failure in the radiation shielding during a solar storm, could be catastrophic. There is also the psychological toll of the monotony of the voyage. The starfield outside changes imperceptibly. There are no seasons, no weather cycles beyond the artificial ones inside. The sense of being trapped, of living in a zoo, could lead to profound existential despair or social pathologies. The Ark must be designed not just for physical survival, but for mental and cultural health. It would need vast communal spaces, virtual reality environments, perhaps even projected skies and horizons to combat claustrophobia. It is a psychological engineering project as much as a mechanical one. From a propulsion standpoint, the Ark would likely use a slow but incredibly efficient and reliable method, like nuclear electric, or even a massive solar sail if it stays within a stellar system for acceleration. It does not need to be fast. It is a home. It might accelerate for decades, coast for centuries, and decelerate for decades at the end. The energy requirements are gargantuan, but if you are building a city in space, you might as well build a massive fusion reactor at its core to power everything. The construction of such an Ark is perhaps the most daunting aspect. It would be a multi-century project in itself. We would need a mature space-based industry, capable of mining asteroids for metals, water and carbon. We would need robotic factories and human crews working in orbit around the Sun, building the Ark piece by piece. It would be a project that spans generations before it even departs, a test of our species' long-term commitment. The launch, when it finally happens, would be a slow, majestic affair. There would be no explosive liftoff. The Ark, already in space, would ignite its engines and begin a gradual, irresistible push away from the Sun. For the first few years, the Sun would still be the dominant feature in the sky. Over decades, it would shrink to a very bright star. For the majority of the journey, the stars ahead and behind would look almost identical. The Ark would be an island of light, heat and life in an ocean of absolute cold and blackness. Its inhabitants would live out their lives tending their gardens, repairing their world, raising children, and telling stories about the legendary blue planet and the promised land ahead. They would be a civilization with a single, all-consuming purpose: survival until arrival. The interstellar Ark represents the most extreme form of escapism. It is not running from a dying Earth, though that could be the catalyst. It is the deliberate choice to transplant a branch of humanity into the galactic garden, to ensure that if one star system fails, the species continues. It is the ultimate lifeboat. But it is also a confession. It admits that the stars are too far for quick trips, that our bodies are too frail for the journey, and that the only way out is to take a piece of home with us and hope it lasts. In the Ark, the solar system is not escaped. It is miniaturized, bottled, and set adrift. The voyagers are silent titanium whispers. The laser-sailed starships are fleeting bullets of data. But the Ark is a shout. It is a whole community, with all its beauty, fragility, and chaos, yelling into the darkness that it exists, and it is moving. It turns the act of escape from a sprint into a marathon, and the runners are not astronauts but farmers, teachers, engineers and children, born into a journey they did not choose, carrying the future in a crafted world. It is, for all its immense difficulty, the most human vision of interstellar travel we have, because it insists on taking all of our baggage, our ecosystems, our societies, and our very nature along for the ride. It refuses to leave our biology behind, choosing instead to build a new shell for it, a shell that must withstand the relentless erosion of deep time. Whether we ever build such a thing is an open question, but considering it forces us to think not as engineers planning a mission, but as architects designing a destiny. The arc is the final, logical conclusion of accepting the scale of the challenge. If you cannot get there in one lifetime, make the spacecraft a lifetime itself. All those concepts, from solar sails to generation arcs, grapple with the same brutal constraint. The speed of light is a universal speed limit, and even a fraction of it requires immense energy and time. But what if we could cheat? What if, instead of moving through space, we could move space itself? This is the seductive dream of the warp drive, the faster-than-light travel of science fiction that has, surprisingly, a tiny foothold in real theoretical physics. It is not a technology, not even a prototype. It is a mathematical possibility that has not yet been ruled out, and it represents the ultimate fantasy of escape. No decades of travel, no generations born and dying in a metal hull, just a short hop by folding the very fabric of reality. The idea was given a formal mathematical framework by physicist Miguel Alcubierre in 1994. He was inspired by science fiction, notably Star Trek, and asked a serious question. Do the equations of Einstein's general theory of relativity permit a way to travel faster than light without breaking the local speed limit for matter? Remarkably, the answer appeared to be yes, in theory. The Alcubierre drive, or warp drive, would not propel a ship through space. Instead, it would create a bubble of flat space-time around the ship. In front of the ship, space-time would be contracted, scrunched up like a rug being pulled into a fold. Behind the ship, space-time would be expanded, stretched out. The ship inside the bubble would be motionless relative to this local space-time. It is the bubble itself that moves, carrying the ship along as if it were on a moving walkway. Since the ship is not accelerating within the bubble, it would not experience crushing g-forces or the effects of relativity. And since space-time itself can expand and contract at any speed, indeed, the universe expanded faster than light in its earliest moments, the bubble could, in principle, move at superluminal speeds. You would be riding a wave in the fabric of the cosmos. This is not some crackpot idea. It was a valid, peer-reviewed solution to Einstein's field of equations. It caused a stir because it showed that faster-than-light travel, in this specific sense, was not forbidden by relativity. The problem, however, shifts from the geometry of space-time to the stuff you would need to create that geometry. To warp space-time in this way, you need what physicists call exotic matter. This is not just weird matter, it is matter with negative energy density or negative mass. Normal mass, like a planet or a star, creates a gravity well that curves space-time inward, like a weight on a rubber sheet. To create the warping for an Alcubierre drive, contracting space in front and expanding it behind, you need the opposite, a kind of anti-gravity effect. This requires negative energy. We see hints of negative energy in certain quantum effects, like the Casimir effect, where the energy density between two very close metal plates in a vacuum is slightly less than the energy density of the surrounding vacuum. It is a tiny, fleeting phenomenon. What the Alcubierre drive needs is vast amounts of this exotic stuff, arranged in a precise shell around the bubble. We have no idea how to manufacture it, or even if it can exist in the stable, macroscopic quantities required. Some calculations suggest the energy requirements are absurdly impossibly high. Early estimates said you would need the equivalent of the mass energy of Jupiter converted into exotic matter. Later refinements suggested maybe you could reduce it to the mass of a spacecraft like Voyager, but that is still an astronomical amount of negative energy, something completely beyond our comprehension or capability. There are other catastrophic problems. To create the bubble, you would need to place the exotic matter precisely where you want the warp field before the drive is turned on. But how do you get it there if you're not already warping space? It is a chicken and egg problem. Then there is the issue of radiation. As the bubble moves, it would collect particles from the interstellar medium. These particles would get swept up in the warped space-time, blue-shifted to extremely high energies, and released in a deadly burst when the drive stops. You would essentially annihilate everything at your destination with a flood of radiation. Some theories also suggest that creating the bubble requires violating what is called the null energy condition, a fundamental principle that many physicists believe cannot be broken. Furthermore, there is the causality problem. Faster than light travel, even via a warp bubble, can potentially lead to time travel and paradoxes, like going back and preventing your own launch. This is a major red flag in physics, suggesting such a configuration might be inherently unstable or impossible. So where does that leave us? The warp drive is a fascinating thought experiment, a loophole in the math that shows our understanding of the universe is not yet complete. It is a playground for theoretical physicists to explore the boundaries of general relativity and quantum field theory. Research continues, with papers published every few years that tweak the geometry, reduce the energy estimate slightly, or explore new constraints. It is legitimate science, but it is science at its most speculative edge. For practical purposes, it is essentially science fiction for the foreseeable future, and likely for centuries to come. It is important to understand this distinction. The Alcubierre drive is not a blueprint. It is a what-if calculation. It tells us that if we had a magic matter with negative mass, and if we could solve the radiation and causality problems, then the geometry of space-time would allow this kind of motion. That is a huge if. It is like saying if you had a frictionless surface and a perfectly efficient engine, you could build a perpetual motion machine. The first part of the statement might be mathematically true, but the prerequisite conditions violate other known laws of physics. The pursuit of the warp drive idea, however, is not useless. It pushes our understanding. By trying to figure out how to make one, we learn more about the fundamental nature of gravity, space-time, and quantum mechanics. It forces us to confront the deepest questions in physics. In a way, the warp drive is the ultimate symbol of our desire to escape the limitations placed upon us by the universe. It represents a hope that there is a back door, a clever trick that a sufficiently advanced civilization could use. But for now, and for any planning we might realistically do, it is a distraction. No engineer is designing a warp drive. No funding agency is building a test rig. It resides in the realm of paper and conferences, not metal and vacuum chambers. When we think about actual missions, about probes we could build in the next 100 years, we must focus on the technologies we have or can extrapolate from. Nuclear thermal rockets, solar sails, laser propulsion, generation ships. These are hard, but they are grounded in known physics. The warp drive sits on the far horizon, a shimmering mirage. It is crucial to be honest about this, because false hope can distort priorities. The public sometimes hears warp drive is theoretically possible, and thinks it is just an engineering problem, like building a bigger rocket. It is not. It is a fundamental physics problem that might have no solution. Our path to the stars will almost certainly be slower, harder, and more profound than a warp jump. It will be a crawl, not a leap. So, while we can enjoy the dream and fund the theoretical research, our concrete plans for escaping the solar system cannot wait for a warp drive. We have to work with the universe as we know it, not as we wish it could be. The warp drive teaches us the final, humbling lesson about escape. The ultimate trap may not be distance or time, but the very laws of physics themselves. And while we have found a tantalizing hint in the math that those laws might be bent, we are nowhere near being able to bend them. For our purposes, the speed of light is a prison wall with no visible door. Our efforts must focus on learning to live with the journey, not on dreaming of a disappearance trick that may forever remain a fantasy. The warp drive is the ghost at the edge of our plans, a reminder of what we wish was true, and a benchmark for just how far our current understanding has to go before we can even consider such miracles. It is the final and most elusive piece of the puzzle, one that we may never fit into place. So if warp drives remain a beautiful mirage, and human arcs are a project for the distant future, how do we explore the exit in a time frame we can actually comprehend? We send machines that can endure what we cannot. We trade flesh and blood for silicon and steel, and we design them not for a mission of years, but for a legacy of millennia. This is the realm of the long-duration probe, a spacecraft engineered to survive the journey through the Oort cloud and into the galactic wilderness. functioning long enough to send back data from realms we will never personally visit. It is a different kind of escape, not of people, but of our consciousness and our curiosity. These probes would be our immortal robotic ambassadors. The first and most fundamental requirement is durability beyond anything we have ever built. The Voyagers are marvels of longevity, but they are already failing after 5 decades. A probe meant to function for 10,000 years must be built to a different standard. Its components cannot be standard electronics. Cosmic radiation and temperature extremes would degrade modern microchips over centuries. We would need to design radiation-hardened circuits, perhaps using different materials like silicon carbide, or even consider mechanical or optical computers. The physical structure would need to be monolithic, carved from a single block of material like titanium or a ceramic composite to avoid the creeping failure of welded joints and screws over millennia. It would need to be passive, with no moving parts that can seize up from cosmic dust or cold welding in vacuum. Or it would need moving parts designed like geological features, with such immense tolerances and lubrication that they could operate once every 100 years without failure. Redundancy is key, but not just duplicate systems. It would need deeply redundant systems, with multiple layers of backup, and perhaps even the ability to reroute its own functions, like an organism healing a wound. Some concepts involve self-repairing probes, using raw materials harvested from the environment. Imagine a craft that, upon entering the Oort cloud, could seek out a comet, land on it, and use the ice for reaction mass or water for shielding, and the dust for raw material to fabricate replacement parts with onboard nanofactories. This is far future technology, but it points to the philosophy. The probe must be an active survivor, not a passive passenger. Power is the next monumental challenge. Radioisotope thermoelectric generators, nuclear batteries on the Voyagers and New Horizons, have a half-life. Plutonium-238 decays with a half-life of about 87.7 years. After 1,000 years, the power output is a tiny fraction of the original. For a multi-millennium mission, you need a power source that either lasts longer or can be replenished. One option is a nuclear fission reactor with a very long-lived fuel core, perhaps designed to run at a very low steady power for centuries. Another is to harness the environment. In the outer solar system, sunlight is useless, but perhaps a probe could use the minuscule energy differences in the magnetic fields of the outer planets, or even the thermal gradient between its warm interior and the cosmic background. These would provide trickles of power, barely enough to run a single sensor and a timer, but perhaps that is all you need for a long dormancy punctuated by brief awakenings. The most speculative idea is a probe that goes dormant for centuries, storing a tiny bit of power until it reaches a specific distance or detects a specific event, then wakes up fully for a short period of observation before returning to sleep. Communication over these distances and times becomes an exercise in patience and precision. The signal from a probe at the outer Oort cloud would take months to reach Earth. It would be incredibly weak. The probe would need a large, fixed antenna, perfectly aligned with Earth, and a transmitter that can focus its signal into an incredibly narrow beam. Even then, receiving it would require a network of massive radio telescopes on Earth, listening constantly. The data rate would be agonizingly slow, perhaps a few bits per second. You would not get live video, you would get a slow trickle of sensor readings, magnetic field strength, particle counts, temperature, and the communication would be one way for the most part. Sending commands to the probe would be pointless due to the years-long round-trip delay. This leads to the most important feature: absolute autonomy. The probe must be its own mission control. It must make its own decisions about when to take data, what to prioritize, and how to manage its own health. It would need an artificial intelligence sophisticated enough to diagnose problems, execute repairs, and adapt its scientific mission based on what it finds, but stable enough that its programming does not degrade or become corrupted over millennia. We are talking about software that must remain coherent and functional longer than human languages last. It might need to periodically rewrite its own core programming from a protected, read-only archive to correct cosmic ray-induced bit flips. The sheer timescale introduces bizarre hazards. Over 10,000 years, the slow accumulation of micrometeoroid impacts, each no larger than a grain of sand, could sandblast the probe's surface, eroding lenses, sensors, and thermal coatings. Atomic particles from the interstellar medium could slowly embed themselves in the material, changing its properties. The probe's trajectory could be subtly altered by the gravitational tugs of passing stars over millennia, requiring occasional autonomous course corrections. Even the star field it uses for navigation will change as stars move relative to each other. The probe's internal clock, likely based on the decay of a radioactive isotope or the vibration of an atomic lattice, must keep near perfect time for 10,000 years, a feat of precision we have never attempted. Why build such a thing? The scientific return would be unparalleled. A probe traversing the Oort cloud could finally map its structure, sampling the primordial material of the solar system. It could measure the interstellar medium far from the sun's influence, giving us a true baseline for the galaxy. It could serve as a gravitational wave detector, with a baseline of billions of kilometers. It could be a deep space observatory, looking back at our solar system or out into the galaxy without the interference of the sun's glow. But its greater purpose is symbolic and strategic. It is a practical step. It is something we could design and launch in the next century that would actually complete the journey of escape within a time frame meaningful to human civilization. While a human crew would take generations, this robotic scout could finish the job and report back, proving the path. It is a testbed for the technologies of survival, durability, autonomy, and long-distance communication. The lessons learned would be directly applicable to any future generation ship. It is also a gesture of very long-term thinking. Launching such a probe is an act of faith in the future, a message to our descendants that we were thinking of them and the questions they might still have. It turns the escape from a human drama into a scientific chronicle. In a sense, these probes are the most realistic form of escape available to us in the near term. We cannot yet send people, but we can send our senses. We can extend our nervous system into the void using machines that do not eat, breathe, or despair. They are the ultimate expression of our curiosity, hardened against time itself. They would be, in effect, immortal. While the civilizations that built them rise and fall, these probes would continue their silent journeys, carrying the dormant intellect of a species that once looked up and wondered what was beyond the light of its star, and had the patience to wait 100 centuries for an answer. They are the opposite of the warp drive's instant gratification. They embrace the slowness, making a virtue of the vast time by building something that can endure it. This path does not require magic physics or societal revolutions. It requires better engineering, deeper redundancy, and a commitment to a project whose full fruits will be harvested by people not yet born. It is a quiet, determined, and profoundly human way to slip the leash. The idea of building machines that outlast civilizations to report back from the void is a powerful one, but it forces a very practical and perhaps uncomfortable question. Why? Why spend the astronomical resources, the centuries of effort, to send a piece of technology on a 10,000-year journey when we have so many pressing immediate problems right here on Earth? This is the paradox of escape, the core conflict between our expansive dreams and our terrestrial needs. It is not a technical question, but a philosophical and economic one that may ultimately be the most binding constraint of all. On one side of the argument stands the imperative of survival and exploration. The case for escape is built on a very logical foundation. Don't put all your eggs in one basket. Earth is a single basket. It is vulnerable. A planet-killing asteroid impact, a supervolcano, a global pandemic, or our own self-inflicted climate catastrophe or nuclear war could devastate or even eradicate human civilization. Having a self-sustaining population elsewhere, whether on Mars, in the Oort cloud, or around another star, is the ultimate insurance policy for the species. It is the biological imperative of dispersal written on a cosmic scale. Furthermore, exploration is in our nature. We climbed mountains and crossed oceans, not just for resources, but to see what was there. The drive to explore is a fundamental part of what makes us human, a source of inspiration and technological spin-offs and profound wonder. To turn inward, to focus only on our planetary concerns, feels to some like a betrayal of our potential, a surrendering of the future. The stars are the next ocean, and not to sail them seems a failure of courage and vision. Proponents argue that the technological challenges of interstellar travel were to catalyze advances in energy, materials, and AI that would benefit Earth enormously. Just as the Apollo program gave us miniaturized electronics and new materials, it is an engine for progress. The other side of the argument is grounded in stark pragmatism and a deep sense of responsibility. The resources required for a meaningful interstellar program are almost unimaginable. We are not talking about a few $1 billion. We're talking about a significant fraction of humanity's total economic output, sustained for centuries. The cost of a single-generation ship project could potentially fund the complete transition to clean energy worldwide, provide universal healthcare and education, end hunger, and solve a dozen other critical global issues. From this perspective, spending that capital on a fantastically risky, multi-generation lottery ticket to another star seems not just impractical, but morally indefensible. It is the ultimate expression of privilege, a project for a civilization that has already solved all its problems, which we clearly have not. There is also the probability of success. Even with our best efforts, the chance of a generation ship arriving safely at a habitable planet after 10,000 years of travel is infinitesimally small. The odds of a catastrophic system failure, social collapse, or simply arriving at a barren system are overwhelming. From a strict cost-benefit analysis, it is a terrible investment. The money would do more tangible good if used to protect our current basket, making Earth more resilient to those very catastrophes we fear. Maybe we are not meant to leave. This is a more subtle argument. Perhaps human biology and psychology are so intrinsically tied to Earth's specific conditions, its gravity, its day-night cycle, its complex biosphere, that long-term survival in space or on another world is impossible. Our urge to escape might be a cultural meme, a romanticized dream fueled by science fiction, not a genuine evolutionary or practical pathway. We might be a planetary species, and accepting that is not a failure, but a maturity. In this view, the real project of the future is not escape, but careful, sustainable stewardship of our one and only home. We should focus on making Earth permanently habitable, a project that itself requires immense global cooperation and technological innovation. The universe, then, can be explored vicariously through increasingly sophisticated robots, like the long-duration probes we discussed. They are cheaper, safer, and can go places we never could. They can satisfy our curiosity without the staggering biological and social baggage. This robotic path might be the rational compromise, allowing exploration without the untenable cost and risk of human missions. This paradox may be what truly keeps us trapped. Not the rocket equation, not the Oort cloud, but a collective subconscious decision that the price is too high. The will to undertake such a project requires a stable, unified and forward-looking global civilization, one that can commit to a goal whose payoff is hundreds of generations away. Our current world, with its short election cycles, economic crises and geopolitical conflicts, seems incapable of such long-term vision. The escape might be technically possible long before it is politically or socially feasible. So, are we choosing to stay? In a way, yes, by default. Every dollar spent on a new fighter jet or a subsidy for fossil fuels is a choice not spent on a Starship engine prototype. Every failure to address global inequality or climate change makes the collective project of a civilization-scale engineering feat less likely. The trap, therefore, might be one of priority. We are choosing to prioritize near-term stability or near-term conflicts over long-term expansion. This is not necessarily irrational. It is hard to sell a public on taxes for a ship their great-great-great-grandchildren might launch when there are potholes in the roads today. Yet the two paths are not entirely mutually exclusive. A civilization advanced enough to build an interstellar ark would, by necessity, have mastered clean energy, closed-loop life support and global cooperation. The technologies are synergistic. You cannot build a generation ship without first learning to live sustainably on a planet. In this light, the dream of escape could actually be the guiding star that forces us to solve our earthbound problems. The goal is not to abandon Earth, but to become the kind of civilization that Asterisk could leave, which is the same as becoming the kind that would never need to. It becomes a test of our maturity. If we can manage our own planet wisely, collaborate globally on immense projects, and think in timeframes longer than a human lifetime, then we earn the option to leave. If we cannot, then we likely lack the cohesion to even attempt it. The paradox forces a question about our identity. Are we explorers by nature, destined to spread, or are we caretakers destined to tend our garden? The answer is probably both, but the sequence matters. Perhaps the first step in escaping the solar system is not building a warp drive, but building a just, sustainable and unified planetary society. The voyage begins at home. The rockets and sails and arcs are just the hardware. The software is our own ability to cooperate across generations. Without that, all the technology in the universe won't get us out the door. So the next time you look up at the stars and feel the pull of escape, remember that the first and most difficult launch pad is right here, in our politics, our economies, and our collective will. The greatest barrier to escape might not be the void of space, but the noise of our own unmet challenges. Solving those might be the propulsion system we need most. So if the true escape begins with mastering our own home and its immediate resources, then we must become experts in using every trick our neighbourhood offers for free. And there is one glorious, elegant trick that has propelled every single one of our farthest travellers, a cosmic sleight of hand that turns planets into slingshots. This is gravitational assistance, or the gravity slingshot, and it is the closest thing to a free lunch in astronautics. It is not a propulsion technology we build, but a navigational technique we steal from the universe itself. It is the reason the Voyagers are where they are, and it represents the indispensable first step in any efficient departure from the inner solar system. To understand it, forget complex engines for a moment. Think of a planet like Jupiter, moving in its enormous orbit around the Sun at a speed of about 13 kilometers per second. Now, imagine a small spacecraft approaching Jupiter from behind, as if trying to catch up to it. As the spacecraft falls into the planet's gravitational grip, it is whipped around the backside in a curved trajectory. From the perspective of Jupiter, the spacecraft leaves with the same speed it arrived, just in a different direction, like a tennis ball bouncing off a moving train. But here is the magic. Perspective is everything. From the Sun's perspective, the stationary observer, the math changes dramatically. The spacecraft has gained momentum from the planet's own orbital motion. It is as if the moving planet hands off a tiny bit of its orbital speed to the spacecraft, like a skater giving a push to another. The planet, being astronomically massive, does not slow down in any measurable way. The spacecraft, however, gets a tremendous boost. This is the gravity assist, a masterful application of the conservation of momentum. It allows a spacecraft to achieve a change in velocity far greater than its own engines could ever provide with the fuel it carries. It is the ultimate leverage. The most famous practitioners are, of course, the Voyager probes. Their entire mission was built around a once-in-a-century alignment of the outer planets that allowed Voyager 2 to visit Jupiter, Saturn, Uranus and Neptune in a single grand tour, using each planet's gravity to hurl it onto the next. Without these assists, the journey to Neptune would have taken decades longer, if it were possible at all with the launch vehicles of the time. Voyager 1 used a particularly strong assist from Saturn, not just to change direction, but to gain enough speed to be thrown upward out of the plane of the solar system on its path to interstellar space. But the Voyagers are not alone. The Galileo mission to Jupiter used a Venus assist and 2 Earth flybys to get there. The Cassini mission to Saturn performed 2 flybys of Venus, 1 of Earth and 1 of Jupiter to gather enough momentum for its journey. The New Horizons mission to Pluto used a gravity assist from Jupiter to shave years off its travel time, reaching Pluto in 9.5 years instead of a projected 15 or more. In every case, the gravity assist was the force multiplier that made the mission feasible. The effectiveness of a gravity assist depends on several factors. The most important is the mass of the planet. Jupiter, the solar system's heavyweight, is the premier gravity assist engine. A flyby of Jupiter can provide a velocity change of many kilometers per second. Saturn, Uranus and Neptune offer smaller but still significant boosts. Even Earth and Venus are used for assists for missions heading inward toward the Sun or to adjust orbits. The second factor is the geometry of the flyby. The closer you can skim to the planet, the stronger the gravitational pull and the greater the possible deflection and speed change. This requires incredibly precise navigation. The third factor is the relative velocity and direction of approach. To gain the most speed, you want to approach the planet from behind in its orbit, so you're essentially being pulled along by its motion. Flying in front of a planet, by contrast, will rob you of speed, which can be useful for slowing down to enter orbit around a destination. This is how some missions achieve orbit insertion at places like Jupiter or Saturn without carrying prohibitive amounts of fuel for braking. There is a related and powerful concept called the Oberth effect. This states that a rocket engine is most efficient when it fires at the point of highest speed in a gravitational field, which is the point of closest approach during a planetary flyby. So the ideal manoeuvre is to combine a gravity assist with a powerful burn of your own engines at periapsis, the closest point to the planet. This synergistic effect can yield even greater final velocities. It is like pushing a child on a swing at the very bottom of their arc, where their speed is greatest, to make them go much higher. For an interstellar mission, the ultimate gravity assist would be a close pass by the Sun itself, a solar oberth manoeuvre. By diving extremely close to the Sun and firing a powerful engine at perihelion, a spacecraft could theoretically achieve a staggering boost. However, the engineering challenges of surviving such a close solar pass and carrying an engine with enough fuel to burn at that critical moment are immense. While gravity assists are miraculous, they are not a magic ticket to the stars. They have a fundamental limitation. They're a local phenomenon. You can only use them where there are massive bodies to slingshot around. Once you leave the realm of the planets, you are done. There are no more boosts. The speed you have after your final planetary encounter is your cruise speed for the next tens of thousands of years. This is why, despite their brilliant use of gravity assists, the Voyagers are still only travelling at about 17 kilometers per second. That is an incredible speed by terrestrial standards, but it is only 0.0057% of the speed of light. It is a crawl on the interstellar scale. A gravity assist is the ultimate launchpad trick, but it cannot propel you across the ocean between stars. It gets you out of the harbour with a good strong push, but the ocean crossing still requires a ship with its own sustainable motive power, or a patience beyond human scales. Furthermore, the geometry of the solar system limits the possible assists. You cannot just swing by Jupiter anytime you want. The planets must be in the right positions. Launch windows for complex multi-planet gravity assist trajectories are rare, sometimes decades apart. This adds a layer of scheduling complexity to any ambitious mission. Yet, for any foreseeable mission to the outer solar system or beyond, a gravity assist will almost certainly be part of the plan. It is the first tool in the navigator's kit. For a future interstellar probe, even one propelled by lasers or nuclear engines, an initial gravity assist from Jupiter could provide a valuable head start, reducing the amount of energy that must be provided by the primary propulsion system. It is a way to maximize efficiency, to use the solar system's own infrastructure to help us leave it. In a poetic sense, the gravity assist is a farewell gift from the planets. As a spacecraft steals a tiny fragment of a world's momentum to fling itself into the dark, it embodies a transfer of legacy. The planet, unaware, continues its eternal orbit. The craft, empowered, begins its long exile. It is a final, graceful interaction with the familiar before the endless monotony of the interstellar void. Mastering this technique is a prerequisite for any serious deep space ambition. It teaches us to think in 3 dimensions, to see the solar system not as a static map, but as a dynamic clockwork of moving masses, and to plot our path through it like a sailor using currents and tides. Before we can dream of warp drives or generation ships, we must become absolute masters of the gravity well, using every nudge and tug it offers. The journey of 1,000 light years begins with a single, carefully calculated swing around a giant. That final, precise slingshot manoeuvre assumes something we often take for granted in our maps of the galaxy, that the target is where we aimed it. But here is the unsettling truth that unravels even the most careful long-term plans. The map is constantly, subtly being redrawn. The stars are not fixed points on a celestial sphere, they are ships sailing the vast ocean of the galaxy, each with its own course and speed. When we point to Alpha Centauri and say it is 4.24 light-years away, we are giving a snapshot, a single frame from a movie that has been running for billions of years. For a journey that takes decades, or even centuries, this motion is a minor correction. For a multi-millennium voyage of a generation ship or a slow probe, it is a fundamental reshaping of the mission. The star you leave for will not be at the coordinates you launch toward. Constellations are temporary arrangements. The Big Dipper, a familiar sight for all of human history, will be unrecognizable in 100,000 years. The stars that comprise it are moving in different directions at different speeds, slowly drifting apart. On the timescale of a 50,000-year journey, the star field behind you and the one ahead of you will be completely different. This means interstellar navigation cannot be a simple case of point and shoot. It is an exercise in predictive celestial mechanics on a galactic scale. You must calculate not only your own trajectory, but the future trajectory of your destination star, accounting for its proper motion through space. And you must be prepared to make corrections along the way, because those predictions, over tens of thousands of years, will have inherent uncertainties. A tiny error in measuring the star's velocity today compounds into a massive positional error millennia from now. The galaxy itself is also moving. Our solar system orbits the galactic centre once every 230 million years or so. The target star is also on its own orbital path around the galactic centre, so their relative motion is a complex dance. For relatively nearby stars within a few hundred light years, their motion is dominated by their individual velocities relative to the Sun, what astronomers call proper motion. Some stars are moving quite quickly relative to us. Barnard's star, for instance, has the highest known proper motion, moving across our sky at about 10.3 arc-seconds per year. That is not much to the eye, but over centuries it adds up. Over the course of a 10,000-year journey, Barnard's star would move a significant fraction of a light year. You would have to aim for where it will be, not where it is. This dynamic reality turns a generation ship's journey into an adaptive, multi-generational navigation problem. The ship's astronomers would need to continuously monitor the positions and velocities of nearby stars, refining their course over centuries. The intended destination might even become less ideal over time, while another star, originally off course, might drift into a more favourable trajectory. The crew might face a monumental decision several thousand years into the voyage. Do we stick with the original target, or do we change course for a new, closer star that our ancestors never envisioned? This could lead to a schism in the ship's society, a conflict between the sacred mission plan and new, updated data. It makes the voyage not just a physical challenge, but a continuous test of decision-making and flexibility across generations. There is a fascinating upside to this stellar motion, however. While it complicates very long-term planning, it also means the cosmic neighbourhood is always changing. Stars approach and recede from each other over millions of years. Right now, the closest known star system is the Alpha Centauri triple system, but in the past other stars have been closer, and in the future others will be. In about 70,000 years, a small red dwarf star called Gliese 710 is predicted to pass within a mere 1 light-year of our solar system, perhaps even penetrating the outer Oort cloud. For a civilization thinking in deep time, these close encounters are like interstellar transfer opportunities. Instead of launching a ship on a horrendously long journey to a static target, you could wait for a target to come relatively closer. Of course, waiting might mean tens of thousands of years, which is not a practical strategy for a short-lived species, but for a long-lived, patient civilization, or for a post-biological intelligence, it could be a viable strategy. You could launch a probe or a seed ship on a much shorter, easier journey to intercept a passing star. This turns the galaxy from a static grid of destinations into a flowing river, where you can sometimes hop onto a passing log rather than swim the entire width. This dynamic galaxy also affects the very concept of escape. When we say escape the solar system, we usually mean reaching a point where the Sun's gravity is no longer dominant. But if another star passes very close, its gravity can temporarily dominate parts of our own Oort cloud, perhaps even capturing some of its icy bodies. In a very real sense, during a close stellar passage, a part of our solar system temporarily becomes part of that star's sphere of influence. The boundaries are fuzzy and dynamic. For a spacecraft on the very fringe, the definition of which star it belongs to could change not because it moved, but because the gravitational landscape shifted around it. All of this underscores that space is not a static backdrop. It is a lively, moving arena. Planning an interstellar voyage is not like planning a road trip across a continent with fixed cities. It is like planning a sailing voyage across an ocean where the continents themselves are slowly drifting. You have a general direction, but you must constantly adjust your sails and your heading based on the currents and the moving landmarks. This adds another layer of profound difficulty to the generation ship concept. The knowledge of celestial mechanics and stellar dynamics must be preserved perfectly, and the ability to make observations and calculate courses must be maintained. If that knowledge is lost, the ship becomes a blind wanderer, its original destination long since moved, with no way to find a new one. For faster, relativistic probes like those envisioned by Breakthrough Starshot, the stellar motion is less of an issue. Over a 20-year journey, even a fast-moving star will only have shifted a tiny amount, well within the targeting capability of a laser-guided system. But for anything slower, it is a paramount concern. It means the escape velocity we need is not just a speed to leave the Sun, but a speed to effectively chase down or rendezvous with a moving target within a reasonable time frame before it moves too far away. The stars are not waiting for us. They're going about their own galactic business. To reach them, we must not only overcome distance and time, but we must solve the problem of a shifting finish line. This makes the dream of escape feel even more like a grand cosmic chess game, where each move must account for the slow, inexorable drift of all the pieces on the board. We are not launching into a still pond, but into a flowing river, and we must learn to swim with its currents or use them to our advantage if we ever hope to reach the other shore. That shifting dynamic map of moving stars presents not just a navigational challenge, but a budgetary one of almost laughable proportions. Because even if we perfectly calculate the intercept course for a star 50,000 years in the future, we then face the most grounded, mundane, and potentially insurmountable barrier of all, paying for it. The economics of interstellar escape are so prohibitive that they transform the endeavour from a scientific or engineering problem into a civilizational one. We're not just talking about an expensive mission. We are talking about a project that could consume a significant portion of humanity's total economic output for centuries. This isn't like building a moon rocket. It's like building a pyramid that takes 1,000 years to complete, with each generation asked to pour its treasure into a hole in the desert for a purpose they will never see fulfilled. Let's start with some rough, staggering numbers. The Apollo program, in today's dollars, cost over $250 billion. The International Space Station cost roughly $150 billion. These are singular, massive achievements that required sustained political will over decades. An interstellar mission, even a modest robotic one designed to simply cross the Oort cloud and report back, would dwarf these figures. Why? Because everything about it is extreme. The propulsion system alone, if it's anything more than a passive solar sail, would be a development project on the scale of the Manhattan Project or the Apollo program itself. Then you need the spacecraft, built to unheard of standards of durability and autonomy. Then you need the launch infrastructure, likely involving heavy lift rockets far beyond anything we have now, to get the components into orbit for assembly. Then you need the ground segment, a global network of giant radio telescopes listening for a whisper from the edge of darkness for 1,000 years. The operational costs over centuries, maintaining that listening network and a mission control center that hands down its knowledge through generations, are incalculable. Initiatives like Breakthrough Starshot, which aims to send gram-weight probes, are estimated to cost tens of billions of dollars for the laser array alone. That's for a fleet of tiny one-shot chips. A single robust probe with a more substantial payload? A human-rated generation ship? The numbers become abstract, entering the realm of trillions or tens of trillions of dollars. To put that in perspective, the entire global gross domestic product is about $100 trillion per year. An interstellar arc project might require spending a noticeable fraction of that every year for a century or more. That is the level of investment we're contemplating. This immediately raises the question of governance. What entity on Earth could possibly undertake this? A single nation? It seems unlikely. The United States could barely sustain Apollo for a decade before political will evaporated. The Soviet Union collapsed. No single nation has the stability, the wealth, or the long-term focus to shepherd a 1,000-year project. A corporation? Even the wealthiest corporations think in quarterly earnings and decade-long plans, not millennia. They might invest in near-Earth space industries, but a pure profit motive for an interstellar mission is non-existent. There is no return on investment for shareholders who will be dead for centuries, so perhaps a global coalition, a partnership of many nations and maybe even private entities, similar to the International Space Station, but on a vastly larger and more permanent scale. This would require a level of international cooperation and trust that is utterly foreign to human history. It would require treaties that bind not just the signatories, but their descendants for 1,000 years. It would need a stable, transparent funding mechanism, immune to economic recessions, wars, and changes in political fashion. The political and public will for such an undertaking is perhaps the rarest resource of all. Politicians are elected on promises that deliver results within a term, or at most a generation. Asking the public to accept higher taxes or diverted resources for a project whose first milestone might not be reached for 500 years is a nearly impossible sell. Public interest and support are fickle, subject to economic cycles and immediate crises. A famine, a pandemic, a war, or a recession would immediately threaten funding, as people rightly ask why money is being spent on a starship when there are problems at home. The project would be perpetually vulnerable to being defunded, becoming a monumental white elephant. This leads to the painful concept of opportunity cost. The money, materials and intellectual capital poured into an interstellar mission are resources not spent solving problems on Earth. With a fraction of a starflight's budget, we could theoretically solve global poverty, provide universal education and healthcare, transition entirely to clean energy, and fund basic science for generations. From a utilitarian perspective, the argument is powerful. Helping billions of living people today is a more moral and practical use of wealth than a fantastically risky gamble on a future that may never come. Proponents of interstellar travel argue that the technological spin-offs would be enormous, but that's a trickle-down argument. One could counter that directly funding research into medicine, energy and agriculture would produce spin-offs more directly beneficial to humanity. The economic trap, therefore, is not just about having enough money, but about the collective decision to allocate it. It forces us to confront what kind of civilization we want to be. Are we one that invests in a glorious shared future project that defines us as a species, even if it means sacrificing in the short term? Or are we a species that focuses on immediate well-being and sustainability, leaving the stars for a far future era of abundance? There is no right answer, but the choice dictates our trajectory. The economics might only become feasible with a radical reduction in costs. This is where space-based resource utilization becomes critical. If we can mine asteroids for metals, water and fuel, if we can build factories in orbit using robotic labour, then the cost of constructing a massive ship shifts from being borne by Earth's economy to being borne by the energy and resources of the solar system itself. The initial investment to build that off-world industrial base is huge, but once established, it could grow exponentially using extraterrestrial resources. In this scenario, the interstellar arc isn't funded by Earth's GDP, it's built by a mature spacefaring civilization using materials and energy from the Moon, Mars and the asteroid belt. The economic barrier then shifts from a financial one to a technological and logistical one. First, we must build that scalable space economy. This is a more gradual, stepped approach. It suggests that escape might only be possible after we have already become thoroughly at home in our own solar system, after space industry is routine and costs have plummeted. So the sequence may be, first, master living and working in space near Earth. Second, industrialize the inner solar system. Third, using those resources, build interstellar infrastructure. The cost-prohibitive nature of a direct launch from Earth may simply be a sign that we're trying to skip steps. In the end, the economics tell a sobering story. We may have the physical means to escape long before we have the financial or social means. The vault door might be unlocked, but we can't afford the train ticket to get to it. This economic barrier intertwines with all the others. The rocket equation demands efficient propulsion, which is expensive to develop. The biological demands require massive artificial ecosystems, which are expensive to build. The timescale demands societal stability, which is expensive to maintain. It all circles back to cost. Therefore, the first real step toward an interstellar future might not be a new engine test, but a new economic model. It might involve creating viable, profitable industries in space that eventually generate the capital and the infrastructure for the great leap outward. Until then, the dream remains just that, a dream constrained not by physics, but by our bank account and our inability to agree on a check that large. The ultimate escape velocity we need to achieve might not be measured in kilometers per second, but in dollars per year, and in the unity of purpose required to spend them on a distant tomorrow. So if the economics are staggering and the physics are unforgiving, perhaps we've been asking the wrong question all along. Maybe how do we escape is a flawed premise because it assumes we need to physically transport our fragile biological selves across that terrible gulf. What if escape isn't about moving atoms, but moving information. What if we've already begun the process without even realizing it? Not by building rockets, but by building transmitters and records. This redefinition changes everything. It suggests that the true prison might not be gravity or distance, but our own insistence that our physical form must make the journey. The most efficient escape pod might not be a ship, but a beam of light. Consider the basic facts of communication. We can transmit information at the speed of light. Radio waves and laser beams travel at the universe's ultimate speed limit. We cannot send a person at that speed, but we can send a complete blueprint of a person, of a civilization, of an entire ecosystem. This is the concept of information escape. Instead of launching a generation ship on a 1,000-year voyage, we could aim a powerful laser at a promising star system and send a compressed data stream containing all human knowledge, our genetic code, our cultural archives, even the precise instructions to build machines that could reconstruct a version of our civilization. A receiving civilization, or even a von Neumann probe we had sent ahead, could use this data to, in a sense, reassemble us. It would be a form of teleportation, not of matter, but of pattern. This is not science fiction fantasy. It is an extension of current ideas in digital preservation and theoretical physics. Your physical body is here, but a perfect scan of your neural connections, your memories, your personality, your consciousness, could be encoded into a signal. That signal travels at light speed. Upon arrival, it could be installed into a synthetic body or a virtual reality. Is that you? It is a philosophical question. But from a practical standpoint, it is a form of travel that completely bypasses the rocket equation, life support, generation ships, and radiation shielding. The passenger experiences no time during the journey. You're deconstructed here and instantaneously, from your perspective, reconstructed there, though centuries pass for the rest of the universe. This shifts the problem from propulsion to data theory, encryption, and the nature of consciousness. But even if we are centuries away from such a capability, a more primitive form of this escape has already happened. Look at the Voyager probes. They carry the golden records. These are not just souvenirs, they're deliberate attempts to cast a message into the cosmic ocean. They contain sounds, images, music, and greetings that define our species. In a very real sense, a curated essence of humanity has already escaped. It is travelling at 17 kilometers per second, yes, but it is travelling. It will outlast our planet, our sun, perhaps even our species. Those records are a seed, a digital spore containing the information needed for another intelligence to know we were here. That is a form of escape from oblivion. Our satellites and radio and television broadcasts have also been leaking into space for over a century, creating a fading bubble of electromagnetic noise expanding at light speed. While these signals are too weak and incoherent to be decoded at interstellar distances, they represent an unintentional ghostly echo of our presence, another layer of informational escape. So perhaps the question, have we escaped, can be answered with a qualified yes. We have launched information carriers. The next step is to do it deliberately, powerfully, and comprehensively. This approach also solves the problem of the moving stars. A laser beam can be precisely aimed at where a star will be in 40 years, because the light will take 40 years to get there. The targeting is straightforward compared to launching a physical object that must adjust its course over millennia. The information arrives when the star is there to receive it. Furthermore, information is immortal in a way flesh is not. It can be copied, backed up, and stored redundantly. A single probe carrying a library of data is vulnerable, but 1,000 laser beams aimed at 1,000 stars increase the odds of survival exponentially. This is the concept of a data diaspora, spreading the essence of our civilization so widely across the galaxy that it becomes impossible to erase. This line of thinking leads to a profound possibility. The ultimate destiny of an intelligent species may not be to become interstellar astronauts, but to become an interstellar intelligence, a pattern of information that transcends its original biological substrate. We might evolve from a carbon-based species to a silicon-based, or even a pure information-based species. Our physical escape then becomes irrelevant. We would escape the solar system by becoming something that no longer needs the specific conditions of a planet, something that can exist in the memory banks of a probe or in the structured energy of a laser beam. The Voyagers in this light are not just scouts, they are proto-cyborg embryos, carrying the first simple digital DNA of our culture. A future more advanced probe might not just carry a record, but an active AI that can rebuild and replicate using the resources it finds. That AI would be our descendant, our ambassador, a piece of our collective mind sent out to survive. This is a different kind of generational ship, one where the generations are iterations of software, not lines of biological descent. The challenges, of course, remain immense. The bandwidth required to transmit a complexity equivalent to a human consciousness is astronomical. The energy needed to send a powerful, focused beam across light years is huge. The ethical questions of creating sentient AI ambassadors are deep, and the very idea of uploading a consciousness is purely speculative. But these challenges are different in kind from the ones that block physical travel. They are problems of computer science, energy collection, and philosophy, not of human biology and multimillennial sociology. They may be more solvable. So, when we look at the night sky and feel trapped, we might be looking with the wrong eyes. We are thinking as animals trapped on a rock, dreaming of building a better boat. But we're also thinking beings who have already invented the alphabet, the printing press, the computer, and the internet. Our superpower is not strength or speed, but the ability to create and transmit complex information. Our escape may lie in leveraging that superpower to its ultimate degree. The physical voyage may be a backup plan, a slow boat for those who insist on keeping their atoms together. But the fastest, most efficient path to the stars may be to finally separate the software from the hardware, to send the message instead of the messenger. In that case, the great project of the next centuries may not be building starship hulls, but building comprehensive libraries of ourselves, developing fault-tolerant data storage that can last for eons, and mastering the technology of beaming that data across the galaxy with perfect fidelity. The launch ceremony for that mission would not be a rocket roar, but the silent click of a switch, turning our entire civilization into a beacon, shouting our pattern into the darkness, into the hope that something or someone will one day understand, and perhaps even welcome us home. That is escape, redefined. It is not about running away from Earth, but about transforming what we are so that Earth is no longer a cage, but a point of origin in a network of light.